Greetings and welcome to the complete lecture for Chapter 11 of Chemistry 222. This chapter involves what's probably one of the chemist's most powerful tools, which is the solution. And in a solution, which is where you have a solute and a solvent, there are lots of properties of solutions that aren't exhibited when you have the solute separately, like by itself, and or the solvent separately by itself. So it's a pretty cool kind of chapter. Also, we'll talk about colloids, which are also useful. We won't talk about them as much, but they are also really cool for chemistry. Let's see what this chapter has to offer. In a solution, you have to remember that there actually are different kinds of solutions. Now, most of the time, what we're going to talk about are homogeneous solutions. And what happens in a homogeneous solution is that you have two different substances and they combine into a single phase. So in the picture in the middle lower part there, probably that's a copper 2 chloride compound. On the right, it's kind of a blue solid. Looks kind of cool, actually. But anyway, when you dissolve it in water, then you make that blue solution, which is what you see in the beaker. And the blue solution has like a stirring rod inside. You want to make sure the solute is totally dissolved. That's an example of a homogeneous solution. Everything comes together. You had a solid, the copper 2 chloride, and water, a liquid. And at the end, the solution looks like a liquid, all right? It's not really a liquid, but it looks like a liquid, all right? That's a homogeneous mixture. You can have a heterogeneous mixture, which is if you'd put, for example, like a rock in water. Most rocks don't dissolve in water, so you can see the rock, a solid, in the water, a liquid, two different phases. So we're going to talk in this section just about homogeneous mixtures. Now, solutions are great examples of what chemists can really do, and that's what we're going to focus on. But depending on actually what happens in the solute, you can also make a colloid or a suspension. So we'll talk about those briefly, but in the back of your mind, just realize most of what we're going to do is talk about these solutions, all right? Solutions are really cool. We encounter them all the time, all right? Solutions are all around. Coffee is my favorite example. Woohoo! I love my coffee, but that's a personal problem you don't need to worry about. There are actually, though, other kinds of solutions that are pretty common to us. So, for example, the air you're breathing right now is actually a solution. You've got oxygen mixed in with a lot of nitrogen to make an air solution, a gas solution, which is kind of cool. And the ocean is definitely a solution as well. All kinds of stuff dissolved in the water, for better or worse sometimes. But anyway, this is the kind of material that we'll be covering in this section. A solution has a solute and a solvent. And the solute is the substance that's being dissolved, quote unquote, and the solvent is the substance that's dissolving the solute. I don't really like either one of those definitions. It's hard to define solute and solvent. But here's the thing, all right? If you take sugar, like in the example there, the next one, and there's different types of sugar, but this sugar is C12H22O11. And sugar is a solid, if you've ever used it, white solid, kind of cool. It dissolves really well in water to make a sugar solution. So on the right-hand side of the arrow there, that C12H22O11AQ, that's the sugar dissolved in water. So when you say sugar solution, you don't say water solution or something like that. Sugar is the exciting part. And that's what I like to think of informally as the definition of a solute. It's the exciting part. So when we're breathing, we think about the air to breathe, not the nitrogen. Air would be the solute and solvent would be nitrogen. In the sugar solution, water is the solvent and sugar would be the solute. But that's my own personal version. You should probably consider the official definitions. Ionic molecules not only dissolve in water, but they also dissociate. And I want to kind of remind you of that. So sodium chloride is a solid just like sugar. And when it goes into water, it dissolves. The solid goes away. You've got one phase. So initially, you'd think you might write NaClAq, which would be sodium chloride dissolved in water. But remember, and this will be important in this chapter, the ionic compounds in water break up into the cations and anions. So sodium chloride is actually Na plus ions floating around in the water and chloride ions floating around in the water. And this will be important to us later on. So just hang tight on that memory. Another thing that's good to remember is the idea of soluble and insoluble. And soluble is when one substance dissolves in another, all right? So the salt water solution, the NaClAq, which breaks into Na plus and Cl minus ions in water, that would be an example of compounds which are soluble. They mix really well together. But there are also combinations of chemicals that are insoluble. They don't mix very well. So for example, oil and water don't mix. Maybe you've heard that expression before. That just means you put oil and water in it. Usually oil floats on the top of the water. It's less dense, all that kind of stuff, but they don't mix very well. So solubility has a big time importance with intermolecular forces that we talked about in the last chapter, and we'll consider that as we go through this section. Chemists a lot of times use the idea like dissolves like to figure out, at least on a rough basis, when things dissolve or not, when they're soluble or not. And the closer the intermolecular forces are to each other, the more likely they are to dissolve. So if you have to guess if two substances will be soluble, if they'll dissolve, or if they're insoluble, they won't dissolve, a really good rule of thumb is to have similar intermolecular forces will dissolve some other similar intermolecular forces. So what I mean by that, polar substances generally dissolve in polar solvents, and nonpolar substances generally dissolve in nonpolar solvents. It's rare for polar substances and nonpolar substances to get along, if you will. That would be an insoluble example. So for example of that, water dissolves really well in ethanol. Ethanol is drinking alcohol, by the way. Just say no, kids. Anyway, ethanol has a polar hydrogen bond to it. It has an OH bond on it. So it gets along really well with water, which has lots of OH bonds. Oil dissolves really well in kerosene, all right? Oil and kerosene are both basically non-polar combinations of molecules, and so they get along really well. However, oil and water don't get along very well at all because oil is almost exclusively induced dipole, the ID you see right there, which means it's non-polar. Water, on the other hand, is incredibly polar with hydrogen bonds. It doesn't usually get along real well with oil. Now, small amounts of oil will dissolve in water. It's true, and this is a problem with pollution, and sometimes people worry about how the water smells because of dissolved substances, but it's a very small amount. And so in general, like dissolves like works really well for chemists, but you should always confirm this with data, stuff like that. So here's a question you might see. It says, which of the following solvents would you expect lithium chloride to be highly soluble? And you can see there's water, carbon tetrachloride, carbon disulfide is C, D, that compound is butane, liquid butane, and E is a compound called benzene. You don't have to worry about any of that. But what I would like you to think about are the types of intermolecular forces happening. So lithium chloride is ionic. It's got a positive Li and a Cl minus, and those are going to be pretty strong forces. And water, as you know, is basically the answer to everything in these classes. But anyway, water, let's not be kind of silly about it. Water has extensive hydrogen bonding, so it's not just dipole, it's extreme hydrogen bonding, if you will. And ion dipole forces form when ions like lithium plus and chloride minus interact with something very polar like water. So big surprise, it's going to be water. Lithium chloride is ionic. Water is polar with hydrogen bonds. So when they come together, it's easy to make the ion dipole force, which is pretty strong. The other compounds down there are essentially nonpolar. So they would use induced dipole forces, which are much weaker, of course, than the ion forces and the hydrogen bonding forces. To further your knowledge of this area, here are some examples. Let's say that I asked you, is vitamin C water soluble? All right. And here's the structure for vitamin C. Now, you don't have to know what all these groups mean stuff, but what I hope you're seeing is that vitamin C has a lot of OH groups on it. And every time you have an OH, that's going to be a site of hydrogen bonding. And water is really into hydrogen bonding, like we've said already. So we would say absolutely. Those 4 OH groups are going to love water because water has OH groups. So vitamin C is a water-soluble vitamin. Here's the structure for vitamin K3. And the question is this one water soluble? And if you look at this structure, which has a lot of kind of cool organic chemistry things that we'll talk about next quarter a little bit. Anyway, vitamin K3 doesn't have any OH bonds or any NH bonds or FH for that matter, although that's not very likely. But anyway, there aren't anything, any of the types of bonds that water would like to make intermolecular force interactions with. Everything on there looks like it's probably a little bit polar, but there's a lot of carbons and hydrogens, and if everything's the same, there's not going to be a lot of polarity. So I would predict that vitamin K3 was not water soluble. This is mostly a nonpolar molecule. The carbon-oxygen double bonds do create a little bit of polarity in the molecule, and there's some other asymmetric ingredients for this molecule. But overall, I don't think there's enough polarity to make this soluble in water, so I would predict this to not be water soluble. And if you look this up in the list of vitamins, vitamin K3 is considered fat soluble. Fats are essentially nonpolar. Nonpolar things get along well with nonpolar things. That's going to be how people classify these. So it all comes down to intermolecular forces once again. That's why they're so important to chemists. Now, electrolytes are important concepts, and I talked about them briefly, but I want to hit this again. If you have a covalent molecule that dissolves in water, like sugar, which I showed you earlier, no problem. Sugar dissolves really well. You put some sugar in water, you dissolve it up. The sugar, the solid sugar, goes away, quote unquote, but if you taste it, you can totally taste the water in the water solution. So covalent molecules dissolve. They are hydrated. The waters go around them, which is no problem. But ionic compounds are different. Ionic compounds not only dissolve if they're soluble, but they also dissociate into the cations and anions. So sodium chloride, as I stated earlier, doesn't just, you wouldn't just write NaClAq, you would write Na plus AQ and Cl minus AQ. They not only dissolve, but they dissociate into the ions, and that will be important coming up here. If you have a dissociated ionic species, and you have these positive and negative ions running around, you can actually conduct electricity through them, which is amazing. So on the upper right-hand side there, I've got 3 examples of different types of solutions, all right? And I want you to focus mostly on the left and the far right. On the far left, it says there's no ions. If you have something covalent, like sugar, and it goes into water, it dissolves really well, but you don't have positives and negatives. And electricity is essentially a series of negative electrons, and negative electrons need positive things to kind of conduct through. So if you don't have any positives and negatives, you won't have any electricity. Covalent molecules are usually considered to be non-electrolytes. That means you don't have any ions. The electrons can't transfer from one side of the solution to the other. No electricity is going to be conducted. And we're going to put in Chem 222 that all covalent molecules do not conduct electricity. So if a covalent molecule dissolves in water, it's considered a non-electrolyte. On the other hand, on the far right, what happens with a lot of ionic compounds is they dissociate almost 100%. Sodium chloride, potassium nitrate, even hydrochloric acid will do this. Strong electrolytes are what usually happens when you place ionic compounds in water. You end up with lots and lots of ions. And if you have lots of ions, the electrons can flow freely, and you have conductivity of electrons. Strong electrolytes. So notice in those pictures, on the far left there, there's no light in the light bulb when it's the non-electrolyte, like covalent bonds, because no electrons can go through. On the other hand, on the far right, you can see that light bulb is very, very bright, all right? Electrons flowing through it, no problem. Now, there are also examples, and this will be important to us more probably in Chem 223 than Chem 222, but there are compounds that are ionic, but they don't dissociate 100%. And if you have one of these, it's called a weak electrolyte. And if you remember from our acid and base discussion in Chem 221, you can have weak acids and weak bases. Weak acids and weak bases don't break up 100% into positive and negative cations and anions. So they're considered weak electrolytes. And as an example of this, acetic acid and ammonia are both weak systems. Acetic acid is a weak acid, ammonia is a weak base. And both of those roughly every 10,000 molecules, one of them will dissociate. So in acetic acid, you'd make an H plus and the acetate ion. Ammonia, on the other hand, will react with water to make ammonium and hydroxide. However, it's only 1 in 10,000 of those that will actually break into positives and negatives. Most of them stay the same. So we'll talk more about weak electrolytes, but for right now, just notice that that light bulb up there, not very bright. You don't have as many ions. The electrons don't conduct as well from one side of the solution to the other. That's where the idea of the weak electrolyte pops in. Okay, so here's a question you might see. It said, how would you classify magnesium nitrate dissolved in water? And you can see there's non-electrolyte, weak electrolyte, strong electrolyte, Gatorade, or more information is needed. Well, first of all, it's not Gatorade. I'll let you know that. And you can absolutely answer this. So magnesium nitrate has a positive magnesium. Nitrate is NO3 minus 1, which is a polyatomic ion, and it dissolves all the time. There were no exceptions for nitrate being insoluble, if you remember from the solubility table. So magnesium and nitrate will break up 100% into magnesium 2 plus ions and nitrate ions. And when an ionic compound dissociates and dissolves, like this one will, it's going to be a strong electrolyte. All right, that magnesium nitrate will not stay together. It's going to break up into magnesium 2 plus and 2 nitrate ions. We're going to get 3 ions out for every magnesium nitrate that goes in, and 3 to 1 is going to create a lot of ions. That thing is going to light up like a Christmas tree. So yep, it's going to be a strong electrolyte.
A strong electrolyte is a compound that ionizes completely in solution. Hydrogen chloride breaks into hydrogen and chlorine ions.
So as a quick review from Chemistry 221, we talked about strong acids, strong bases, weak acids, and weak bases. And why that's relevant now is that all those strong acids will dissociate 100% into cations and anions. So if you have a strong acid or a strong base, they're going to be strong electrolytes. Also, all of the compounds that dissolve, that are soluble, all right, and according to our solubility guide there in the upper right, all of those are going to be strong electrolytes. So you can see up there in the right hand corner, the soluble ions always will have usually sodium, potassium, ammonium, nitrate, perchlorate, things like that. We also talked about how chloride, bromide, and iodide are usually soluble except for with silver, mercury, lead, stuff like that. Anything that's soluble, you put AQ next to, and those will break up 100% into cations and anions. So there's a lot of strong electrolytes out there. All the strong acids, all the strong bases, and all the ionic compounds that dissolve in water. So again, those 5 strong acids and 3 strong bases, pretty important for lots of reasons. Here's another reason: they're going to be strong electrolytes. Now, all of the weak acids and weak bases, though, those are going to be weak electrolytes. And if something is insoluble, so for example, if you have barium carbonate, for example, barium carbonate has a carbonate, and most of the time carbonates are insoluble unless they're with ammonium or the alkali metals, which is rare. That's going to be an example of an insoluble compound. That's not going to conduct electricity. It has to dissolve first. Barium carbonate doesn't even dissolve in water, at least according to what we've learned so far.
A weak electrolyte is a compound that only partially ionizes in solution. Some hydrogen ions dissociate from acetic acid molecules, but others may rebond at the same time. Some compounds that dissolve in water, such as ethanol, do not dissociate into ions at all. Such compounds are called non-electrolytes.
Okay, a lot of information in those 2 videos, so let's break this down. So what's really important here is that we have strong electrolytes, weak electrolytes, and non-electrolytes. And the strong electrolytes, which we talked about in the previous page, are basically strong acids, strong bases, and ionic compounds that dissolve well in water. And you can use the solubility guide to do that. Now, weak electrolytes are basically going to be weak acids and weak bases. And on the right-hand side there are several examples of both weak acids and weak weak bases. If you see an acid or a base, and it's not one of the strong acids and strong bases, you can definitely assume in this class that it's going to be a weak acid or a weak base. And that means it's going to be a weak electrolyte. So as an example of that, if you had, say, 10,000 molecules of ethylamine down there, which is a strange base, but anyway, 10,000 molecules of that, you would have 1 in 10,000 of the ethylamines react with water. It would make some hydroxide, and you'd have some kind of weird other conjugate species, which we'll talk about in Chem 223, but only 1 in 10,000 of those do that. So it's considered a weak electrolyte. It doesn't conduct electricity very well, and all the weak acids and weak bases will do that. And then finally, there are non-electrolytes. Those would be the sugar solutions and my beloved coffee. And if you have ethanol, drinking alcohol, and water, stuff like that, those are all covalent molecules that dissolve in water. And water is pretty good about doing some of them, like vitamin C, for example. All of those are non-electrolytes because you don't have positives and negatives running around. And if you don't have positives and negatives, you can't have electricity go through, and there's no light in the light bulb. And that will be important for us coming up here.
When nickel chloride is added to water, it dissolves readily. Because more nickel chloride could be dissolved in this solution, the solution is called unsaturated. When solutions of lead nitrate and potassium iodide are mixed, solid lead iodide precipitates from solution. The liquid remaining in the test tube is a saturated solution of lead iodide. Whenever a precipitation reaction occurs, the solution surrounding the precipitate is saturated with the product of the reaction.
So 2 terms we're going to use to describe what happens when compounds dissolve in water are saturated and unsaturated. And to figure out when something is saturated or unsaturated, we need to know about the solubility. So what we're talking about here is when you have a compound that dissolves in water, how much of the solute can dissolve in water, all right? And the solubility is literally some kind of maximum amount that can be dissolved in that amount of solvent at that given temperature. We'll see later that it's temperature dependent. So as an example, if you take the green nickel 2 chloride and you dissolve it in water and you stir it up, all the solid goes away. That's considered an unsaturated solution because you could probably put more nickel 2 chloride in there, stir it up, have it dissolve, go away. All right. So an unsaturated solution just means you can add more solute to the solvent that you have and it'll keep dissolving. And there's a temperature dependence too, but that's not as important. So unsaturated means there's more room for solute to dissolve in the amount of solvent that's present in your solution. Now, there comes a point, though, where you can't add any more solute, and that's when you have a saturated solution. So you can think about all of the solvents as having a capacity for dissolving solute, and once that capacity is exceeded, like it was there in the yellow solid in the upper right-hand corner, then you have a saturated solution. So in a saturated solution, you will see the solid. You can stir and stir and stir, and it won't dissolve back into the solution. It stays as a solid. And all compounds have a saturation point. This will be something we'll talk about more in Chem 223, how to predict when you get to the saturation point. But it's just something to consider. But if you see a solid, then that means that your solution is saturated. So insoluble compounds have a pretty low saturation point because it's easy to see the solids and stuff that form. You can't dissolve and make them go away. We'll come back to this in a later lecture.
When supersaturated sodium acetate is poured onto a few grains of solid sodium acetate, the amount of sodium acetate dissolved in excess of the saturation point precipitates, forming a solid. Some of the liquid solution, which is now simply saturated, becomes trapped within the solid.
There is also what's called a supersaturated solution. And this is kind of a specialized application, but it can be useful when you're trying to crystallize compounds that you make out of solution. But anyway, in a supersaturated solution, these are always unstable. And usually what happens is they'll heat up a solution to a warmer temperature. And the amount of solute that dissolves depends on not only the amount of solvent, but it does depend on the temperature. And generally, energy at warmer temperatures, you can dissolve more solute at a warmer temperature than you can at room temperature. So if you have one of these supersaturated solutions, usually the solvent has been heated up. You can add a lot of solute, and then if you cool it down and you disturb it, like if you have a little seed crystal to get it started, then all of a sudden you start making solid like crazy, and you can make some kind of cool geometric structures. Anyway, this is kind of a specialized application of solutions, but if you hear about supersaturated solutions, they are a little unstable. You can't just carry them around and stuff like that and expect them to do it. And once you disturb them, they will start saturating out right away. And sometimes the results are quite impressive, as you can see from that wild kind of structure there. Now, we've talked mostly so far about solutes and solvents where the solute was a solid, but you can also have gases dissolved in liquids too. That's not a problem. And generally speaking, gases are usually more soluble in liquids at lower temperatures. As you get to higher temperatures, then the gases have extra energy and they're able to essentially break away from the liquid. That's what I think about. So a lot of times, if it's a hot day, you want to open up a carbonated drink, a Coke product or beer if you're 21 and over, 19 in Canada, but I know that joke gets kind of old after a while. But anyway, carbonated drinks are usually more bubbly if they're in the refrigerator, all right, because colder temperatures, the gases dissolve better. And as you start warming it up, then the carbon dioxide comes out, that fizziness happens, and it usually makes the drink more attractive to people. Not always, but most of the time. So Henry's law is actually a mathematical relationship that talks about how soluble a gas is. And solubility, which gets the symbol capital S with a little g, is the solubility of the gas. And it depends upon a Henry's law constant. And these are things you either determine or you can look up in a book, something like that. And it does depend on the partial pressure of the gas over the liquid. And the more partial pressure you have, the more soluble the gas is in the liquid. On the other hand, if you don't have a lot of the gas above the liquid, then the gas is not very soluble. Henry's law is used a lot by the soft drink industry to kind of make the best combination of carbonation with their drink possible.
When a can of soft drink is opened, a whooshing sound is heard, and the solution begins to release bubbles. The escaping gas is carbon dioxide. Henry's law explains why the gas leaves the liquid only after the can is opened.
So when you pop the top of a soft drink or some kind of beverage like that, you hear that hissing sound and stuff, and you pour it, and inevitably what happens with me is the liquid goes over the container side of the glass. But anyway, that's just me being clumsy. But anyway, the idea is that if the external pressure drops, then the solubility goes down. So on the right-hand side, look at those two pictures right there. Let's look first at the bottom one. That represents a high pressure, like they're pushing down on it. And you can see that there's lots and lots and lots of little purple gas molecules dissolved in the liquid. There's some above the liquid totally, but there's a lot of them beneath it. Well, in the upper example, we haven't totally popped the top, but we have lowered the pressure. And you can see how there are fewer of the purple gas molecules in the liquid. Most of the purple gas molecules are over the liquid. So as the pressure goes down, the gas isn't as soluble. You don't have as many gas molecules in the liquid, which is kind of interesting. There's an example of a Henry's law constant for oxygen, 1.66 times 10 to the minus 6 molar per millimeter of mercury. Millimeter of mercury is what the pressure of the gas is usually measured in. Remember, a millimeter of mercury and a torr are the same thing, and 760 millimeters of mercury equals an atmosphere. And the big M, the molarity then, is the solubility of the gas in the solution, which is kind of cool. So here's a kind of question you might see. It says, after a can of Diet Coke is removed from the refrigerator, opened and left to stand a while, which of the following best describes the changes that cause the soda to go flat? And going flat, again, just means that it doesn't have any more carbon dioxide in it, basically. But anyway, here's the different possibilities. It says lowering the carbon dioxide pressure over the solution and raising the temperature is what happens to make the flatness appear. You could also say lowering the CO2 pressure over the solution would be a possibility. Lowering the temperature would be one answer. And you can increase the salt content. Well, first of all, on D, we're not adding any salt, so that doesn't make any sense whatsoever. However, if you think about it, if you open the can, you're lowering the CO2 pressure over the solution, and that's going to make the CO2 rush out. In this example, you're also allowing the Diet Coke to stand at room temperature for a while, and that's going to raise the temperature. And both of those things will definitely affect how much CO2 is present. So if you raise the temperature and open the can, it's going to go flat a lot faster. If you open the can at a lower temperature, it wouldn't go flat quite as quickly. You can kind of see how this works. And people that work in the soft drink industry often have to think about these kind of considerations when making their soft drinks. Gases in liquids become less soluble generally as temperature goes up. All right. And again, you can think about gases as having more energy, so they escape, et cetera, et cetera. However, generally, solids and liquids become more soluble generally as the temperature increases. So in that graph right there, you can see that almost all of those compounds, sodium nitrate in the upper left, calcium chloride underneath it, lead 2 nitrate, et cetera, almost all of them are going up as the temperature, the x-axis, increases. However, that's not all the time the case. So down there in the lower right-hand corner is this weird cerium sulfate compound. That's an example of a compound that becomes less soluble as temperature goes up. And we'll talk about this more in Chem 223, why that kind of thing is possible. However, in general, ionic compounds become more soluble in water as the temperature goes up. Liquids in liquids can be infinitely soluble if they have similar intermolecular forces. So, for example, water in ethanol, water in acetone, all these kind of similar things, if they're liquids, they should be able to dissolve almost forever. They're considered to be miscible. Miscible is a term that means that they get along really, really well. They're usually for liquids. And if they're similar intermolecular forces, they should just dissolve as long as you can. So there's lots of examples of this. If your car has a radiator, it probably has some kind of antifreeze in it, and that antifreeze is essentially a hydrogen bonded containing species that dissolves well in water. You can pump that up as long as you want, no problem. They're very miscible. Immiscible solutions usually are liquids with different intermolecular forces. So again, that oil and water example we mentioned earlier, oil is basically induced dipole. Water is hydrogen bonded. Those two forces don't get along. So in that glass container right there, the top layer is some type of oil. The bottom layer there is like water. It's clear. And they don't get along very well because they have different intermolecular forces, which is kind of cool. So miscible just means liquids dissolve really well in each other, and you can basically add them, and you'll never have any problems. On the other hand, immiscible means they don't have similar forces, and they generally don't dissolve very well. Solutions are important to chemists because solutions have properties that the individual solutes and solvents do not. And if you have a solution, you can take advantage of what are called colligative properties. And colligative properties are properties of solutions. Now, the colligative properties, when you have a solution, affect the solvent, and that's kind of wild here. So if you hear about a solvent that's having its vapor pressure lowered, that's an example of a colligative property. You can also hear about a solvent having its melting point going down or decreasing, its boiling point going up or increasing, and you can also hear about a solvent experiencing what's called osmosis or osmotic pressure, same thing. Those are the 4 colligative properties, and they're properties only of solutions. So you have a solute or a solvent separately, none of these are going to apply. But in a solution, the solvent is affected. The vapor pressure goes down, the melting point goes down, the boiling point goes up. Osmosis is possible, osmotic pressure, kind of crazy. Colligative properties, these properties of solutions, they depend on the number of solute particles relative to the solvent particles. It doesn't really matter in this section on the kind of solute particles, and this is a weird concept. But for example, you can have an acid, all right, like hydrochloric acid, and it will have colligative properties, and so will sodium chloride, which is not acidic or basic or anything like that. And it really just depends on the number of solute particles, like the number of NaCl's or the number of HCl's. It doesn't matter if it's a strong acid, strong base, etc., etc. We just want to know the number of solute particles. So why this is important to chemists is that so far we have used for a concentration unit molarity almost exclusively. Molarity is moles of solute over liters of solution. And moles of solute over liters of solution has nothing to do with the number of solute particles relative to solvent particles. Moles of solute is related to particles of solute, but liters of solution doesn't have any relationship, more or less, to number of pieces, number of particles. So we're going to need some new concentration units in this section. And these concentration units are not hard if you spend the time figuring out how they work. And I highly encourage you to spend some time with these new concentration units, get them under your belt, get them figured out, and then you'll have no problem when we get to the colligative properties. So we'll look at these new concentration units first, and then we'll come back to vapor pressure, decreasing, melting point, decreasing, boiling point, increasing, etc., etc. The first of our new concentration unit is called mole fraction. And mole fraction, for example, if you have a solution of A, B, and C, for example, acetone, ethanol, and water, and you wanted to find the mole fraction of the acetone A, then you would, to find the mole fraction of acetone, you would take the moles of acetone, put that in the numerator, and then in the denominator, you'd put the total moles. So it would be moles of acetone plus moles of ethanol plus moles of water. So it is literally a fraction, all right? It's not a percentage, it's just a fraction, and it's moles of what you're looking at divided by total moles, essentially. The second unit we're going to look at is called molality. And molality sounds a lot like molarity, and I apologize for that, I'm just the messenger here, but there are a lot of differences. Molality, which has the symbol little m, is moles of solute over kilograms of solvent, all right? So little m, moles of solute over kilograms of solvent. Molarity, capital M, moles of solute on the top, just like molality, but in the bottom you have liters of solution. And so that makes it quite a bit different than molality, which is kilograms of solvent, not liters of solution. We'll come back to this in a little bit. Mass percent is the third type of concentration we're going to look at. And the mass percent will just be grams of the solute divided by total grams. And you could also have grams of solvent over total grams if you wanted the mass percent of the solvent. Most of the time we'll think about mass percent of the solute. These three are our new types of units. They will complement molarity, but they are different from molarity. Molarity has a liters of volume term, and all of these are either moles or grams, or kilograms for that matter. So there's going to be some differences. I highly recommend you check out the solution calculations handout. It will have more information on how to convert from one of these units to the other. But let's look at some examples here of how you would convert from one to the other and figure them out. In this question, we have 1 mole, 60 grams, of urea, which there's the compound formula, and it's in 15 moles, 270 grams, of water. And the question is, what's the mole fraction of the urea? So mole fraction, which by the way gets that symbol, looks like a capital X. Technically, it's a chi. It's a Greek letter. I don't care if you write an X, but that's technically what it is. Anyway, the mole fraction of urea will be moles of urea on the top divided by total moles on the bottom. So for this problem, that would be 1.0 moles on the top, and we'll divide it by total moles, which is moles of urea plus moles of water. So on the bottom, you'll have 1 plus 15, or 16. On the top, you'll have just 1. Mole fraction will equal 1 over 16. Don't leave it in fraction form. You want to calculate it. 0.063 would be the mole fraction of the urea. So again, not really hard to figure out, just kind of tedious, and you have to figure out the definitions, jazz like that, but nothing you can't handle. So let's assume we have 62.1 grams of ethylene glycol, and 62.1 grams is the same as the molar mass of ethylene glycol. So 62.1 grams divided by 62.1 grams per mole gives you exactly 1.00 moles. So 62.1 grams or 1.00 mole of ethylene glycol is placed in 250 grams of water. We can use this information to calculate the mole fraction, that chi, molality, which is little m, and the mass percent of the ethylene glycol. And there's the formula up there. And by the way, you can see the ethylene glycol has not just one, but two OH sections, so it gets along really well with water. They're very miscible, all that kind of stuff. First thing you're going to need on these kind of problems, you're going to need grams of solute and solvent and moles of solute and solvent. So if you look at that data, 62.1 grams, that's the grams of the solute, the ethylene glycol, and 1.00 moles, that's the moles of the solute. So we've got grams and moles of solute, no problem. But there's only grams of solvent, 250 grams of water. So we do need moles of water. So if you take 250 and divide by the molar mass, which is about 18.02 grams per mole, you should get 13.9 moles of water. If you don't get 13.9, let me know. All right, this is really important, but you need grams and moles of solute and solvent. And by calculating 13.9 moles, now we have moles of solvent. And now we can start just putting things together. So let's do the mole fraction of the ethylene glycol first, all right? So mole fraction of ethylene glycol, moles of the ethylene glycol, I'm just abbreviating glycol, divided by total moles. So 1 divided by 1 plus 13.9 would be like 1 divided by 14.9. Always calculate it, don't leave it in fraction form, 0.0672. That's the mole fraction of the solute. Now, as an extra bonus, whoa, I know you're excited, but anyway, as an extra bonus, we can calculate the mole fraction of the solvent pretty readily, because mole fraction of solute plus mole fraction of solvent will always equal 1. So even though I didn't ask for it, I wanted to highlight it here. Mole fraction of the solvent water will be 1 minus the mole fraction of solute, 0.9328. So that's just a little word to the wise. If you have to find the mole fraction of the other component, 1 minus the mole fraction of the first one equals the mole fraction of the second one, assuming you have only 2 components, of course. Molality is moles of solute over kilograms of solvent. Now, it's really important to know there's 1,000 grams per kilogram. So 250 grams divided by 1,000 grams per kilogram is 0.250 kilograms of water. We'll do that a lot, so make sure you've got that ready to rock and roll. So molality, moles over kilograms, that comes out to be 4.00 molal. Molal is how you say it. It sounds kind of weird, but that's how you say it. And then finally, the mass percent, the ethylene glycol would be the grams of ethylene glycol divided by the total grams. So 62.1 grams divided by 62.1 plus 250. When you figure that out in your calculator and multiply by 100%, 19.9% ethylene glycol. And then if you wanted to find, hint, hint, the mass percent of the solvent down there, well, 2 components always equals 100%, in this case anyway, assuming you have 2 components. So 100% minus the mass percent of the ethylene glycol will give you the mass percent of water. So 80.1% would be the mass percent of water. No problem. Lots of hints here, but if you see how this plugs together, none of this stuff is any more than algebra, and that's all stuff you can do. If you have questions, of course, on anything, let me know. So here's a question. We have 92.0 grams of ethanol, CH3CH2OH, in 270 grams of water. What's the mass percent of the ethanol? All right, no problem. So you'd start with the 92.0 grams of solute in the numerator. You would divide by the total mass in the solution. So that comes from 2 sources. That'll be 92.0 plus 270 in the denominator. And this one is a percentage, so whatever the number that comes out, we'll multiply it by 100%. So 92 divided by, parentheses, 92 plus 270, parentheses, times 100%, 25.4%. no problem. And again, if you wanted to find mass percent of water, 100% minus 25.4 would give you the mass percent of water, and you're good to go. Converting between molality, mole fraction, and mass percent is relatively straightforward. Like I said, you're going to need grams and moles of solute and solvent. And if you have all of those, and you remember that 1,000 grams equals a kilogram, you can convert from one to the other pretty straightforward. And we'll do this in the problem set and stuff like that. But remember that in chemistry, the king of the concentration units is definitely molarity, capital M. And molarity is used more than anything else when it comes to solutions at Mount Hood and every place. Now, moles of solute isn't too bad because, for example, in molality, you need moles of solute. But a liter of solution, liter is a volume, and all of the other units, molality, mole fraction, mass percents, use moles or grams. So to go from a moles or grams specifically, into a volume, you're going to need the density of solution, all right? And the density of the solution, or solution density, will have units of grams per milliliter, grams per centimeter cube. And recall that a milliliter is equal to a centimeter cube, so it's no problem. So what I want to do here is show you an example of how you can go from one of the three types of units, molality, mole fraction, and or mass percent, and turn it into molarity. Remember that a solution is solute plus solvent. So if you had 100 grams of solute and 200 grams of solvent, then the solution would have 100 plus 200, or 300 grams of solution. We'll use this kind of concept here in a little bit. We have a 10.7 molal aqueous sodium hydroxide solution. And let's stop right there. Aqueous means the solvent is water, NaOH is the solute, and the solution is 10.7 molal. So that means that in 1 kilogram of solvent, we would have 10.7 moles of NaOH. So we want to convert 10.7 molal into mole fraction, mass percent, and molarity. And notice here it's giving us the solution density, 1.33 grams per centimeter cubed. All right, no problem. So on a problem like this, what I would do is get molality, mole fraction, and mass percent cleaned up right away, because they're usually a little bit easier. But in order to do these problems, you have to know kind of where to start. And if you have a molality that you're given, what I would do is assume you have 1 kilogram of solvent. Now, if it's 10.7 molal, that means 10.7 moles of solute per kilogram of solvent. So in 1 kilogram of solvent, which would be 1,000 grams of water, you would have 10.7 moles of solute, 10.7 moles of sodium hydroxide. So molality, if you're starting, assume a kilogram of solvent. Now, from there, remember you need grams and moles of solute and solvent. So we can take that 1,000 grams of water, divide by 18.02 grams per mole, the molar mass of water, to get 55.5 moles of water. We're also going to need grams of solute, so 10.7 moles of sodium hydroxide times the molar mass of NaOH, which is about 40 grams per mole when you figure it out. That little -1 there just means that it's per mole, if you remember. Anyway, that comes out to be 428 grams of NaOH. So the mole fraction of sodium hydroxide, moles of NaOH divided by moles NaOH plus moles of water. And you can see, just plugging those values in, that's 10.7 moles NaOH divided by parentheses 10.7 plus 55.5, the moles of water, mole fraction 0.162. The mass percent of sodium hydroxide would be the grams of NaOH divided by the total grams times 100%. So 428 grams NaOH divided by 1,000 plus 428, and all of that times 100%, 30.0% NaOH. Now, we haven't used the density of the solution at all at this point, because again, mass percent, mole fraction, molality, it's all about moles and grams of solute and solvent with the 1,000 grams per kilogram thing thrown in. On the next slide, we will use the density of solution to figure out how many liters of solution we have, and we'll talk about that on the next piece here in just a second. Okay, so when you're dealing with molarity, you have to remember that you're looking for liters of solution. And in the last slide, we had a kilogram of solvent. That's what our assumption was. And a kilogram is 1,000 grams of water. And we calculated that we're going to have 428 grams of solute, sodium hydroxide. So what that means here is that our grams of solution will be 1,000 plus 428, 1,428 grams of solution. So notice that you add the grams of solute to the grams of solvent. That gives you the grams of solution, 1,428 grams of solution. Woohoo! Now, why that is kind of a woohoo moment is because you can take the grams of solution and the density of solution, which is that 1.33 number up there, to find the volume of the solution. So in this slide, grams of solution, 1,428, divided by the density, 1.33 grams per centimeter cubed. The grams cancel out. You've got centimeters cubed. A centimeter cubed is the same as a milliliter. 1,070 milliliters is how much volume of solution we have. And if you divide that number by 1,000, 1.07 liters. So we just found the liters of solution right there, which is pretty cool. If you take the total mass of the solution and divide by the density, that'll give you the volume. A centimeter cubed and a milliliter are the same. And then dividing that by 1,000, 1.07 liters. Now, why that's kind of cool is that in a kilogram of solvent, you have 10.7 moles of solute. So we said earlier, 10.7 moles of NaOH is what we've got, and we're standing by it. That number divided by our new 1.07 liters, that's going to give us molarity. So the molarity of the NaOH here, 10.7 divided by 1.07, 10.0 molar. So what we have just done there is we took a molality and turned it into a molarity. And we needed the total grams of the solution, which is this 1428 number right there to do it. All stuff you can do. So you can see this is just kind of a path you got to follow, and the more you follow the path, the easier it is, all that kind of jazz. But it is important because molarity is the king of the units. It's used more than anything else, and it's nice sometimes to translate molality into molarity or vice versa. So here are some tips on converting concentrations in this section. And I know it's a little weird, but the more you get used to it, the better it is. You're always going to need grams of solute and grams of solvent, all right, to figure out the different pieces. And grams of solute plus grams of solvent equals grams of the solution. So you can use the density of the solution to go to volume, stuff like that. So here's some tips in converting these different ones from one to the other. And it's all stuff you can do. It's just a little tedious. And the more you practice, the easier it'll get. But you're always going to need grams of solute and grams of solvent. And if you have both of them, you can combine them to get grams of the solution. And that's how you find the volume of solution. If you're going to molarity, that's where the density pops in. Likewise, you only need the density of the solution if you're converting to or from molarity. If you're just doing mole fraction to molality, for example, you don't need the density. If you're starting with molality, you want to assume that you have a kilogram of solvent. And then whatever number you have for molality, that's going to equal the moles of the solute. And that's what we did in the last example. Now, if you're starting with mole fraction, you want to assume you have 1 mole total. So whatever number for mole fraction you have, that's going to equal moles of the solute. And then 1 minus the mole fraction number you're given is going to be the moles of solvent. And from the moles, you can go to grams, and you can do all the other things from there, no problem. If you're starting with mass percent, you want to assume you have 100 grams total. Then whatever mass percent number you're given, that equals the grams of the solute, and 100 minus the mass percent will give you the grams of solvent. And once you have grams of solute and solvent, you can go to moles of solute and solvent, etc., etc. If you're starting with molarity, the capital M, then you want to assume you have 1 liter of solvent. So whatever molarity number you're given, that equals the moles of the solute. You can can turn liters of solvent into milliliters. And the density will allow you to find the grams of the solution, and moles of solute, you can find the grams of solute. So grams of solution minus the grams of solute gives you grams of solvent, and you're good to go. So again, I highly recommend that you look at the solution calculations handout. There are examples, both a worked example and one to do on your own with the answers that you can practice, all right? Practice makes perfect with this kind of stuff. It's all material you can conquer, but it does take a little bit of practice, so check it out, okay? Another kind of concentration unit that I need to mention in this section is what's called a parts per million. And parts per million, and there's different kinds of parts per million, by the way. There's also parts per thousand and parts per billion. But these are used for very, very dilute concentrations of solute. And they're mostly used by people studying the environment, so like environmental chemists, biologists, geologists sometimes, stuff like that. And for example of how this works, 1 part per million, ppm, would be 1 gram of the substance, solute, whatever, in a sample with a total mass of 1 million, which would be 10 to the 6 grams. So 1 gram of substance in 1 million grams is going to be pretty small. Now, a lot of times with parts per million and parts per billion, etc., they assume the density of water is exactly 1 gram per milliliter. So they a lot of times will interconvert one to the other. If you had, for example, a parts per thousand, it would be you divide it by 1,000, 10 to the third grams. If you had a parts per billion, ppb, that would be dividing by 10 to the 9th grams, a billion grams. And once in a blue moon, I've seen even a parts per trillion, which would be dividing by 10 to the 12th, but that's rare. Anyway, in lab, we have used parts per thousand, but that's different than this parts per thousand. In lab, our parts per thousand is a measure of precision, how close the measurements are to each other. So if you have 2 or more measurements, you can do a parts per thousand analysis to get a number, and the smaller the number says that your values are closer to each other. This parts per thousand in this slide is a concentration unit. It's like a gram of, say, silver in 1,000 grams of water, something like that. So it's a different kind of parts per thousand. The name is the same, but there's definitely different applications. These are pretty important. The picture in the lower right-hand corner shows different water samples at different concentrations of parts per million. And you can see that 0 parts per million and 1 and 10 look pretty good, but when you start getting to 100, it looks kind of hazy. And by 1,000 or 10,000, then you see real like particulate matter inside there. So it can be super important. They're used a lot of times in legal disputes as to what safe drinking water is, for example. There was a big thing about arsenic in drinking water, which is more than I can go into now. But anyway, a lot of times this is where you see these kinds of units. We won't use them extensively in this class, but I do want you to hear about them in case you'd happen to run into them or maybe use them in a future career choice.